Hi, in this lecture, we will talk about error estimation for the finite element method. So in finite element, we can have different kinds of errors. One error is domain approximation error, which often happens because we cannot really, in complex geometries, capture the, the morphology of the geometry with a discrete mesh. So approximating a geometry with a discrete mesh leads to domain approximation error. We also have quadrature errors in numerical integration of the terms in our weak forms, round-off errors due to computer calculations. And finally, perhaps the most relevant one to finite elements theory is the approximation error, where we essentially hypothesize in finite element that the true solution could be approximated across each element using this equation with the shape functions that we prescribe. So essentially, by defining the shape functions to be linear or quadratic, we are constraining the space of all possible solutions that we can have in each small element. And that assumption is what leads to approximation error. So that defines how well we can approximate the solution, because we're really limiting ourselves to those basis functions defined through these shape functions. Okay, now we can define absolute errors. We can define relative errors, which these errors are field variables. They're functions of space, right? So to turn them into a single error value, we can calculate the norm. For example, the infinity norm is the maximum value of these errors. We can do the L2 norm, or we can do an energy norm motivated by the Sobolev space that we talked about previously, where we can calculate the error, as a sum of the errors in the values as well as their gradients. Now, an important consideration here is the accuracy of the solutions that we are obtaining. So we say in finite element that the solution converges to a true solution if the error characterized by some norm between the solution UH, or discrete solution, with respect to a true solution is bounded. It's less than some constant times h, our mesh h size, or some characteristic length representing our elements, raised to the power p. So if you look at this equation, you can see if you make your mesh finer, h smaller, the error becomes smaller. And also if you have higher rate of convergence, if p is larger, because h is small values, so then you're also going to get a more accurate representation. So now to reduce the error in solutions, we have two choices. We can do what's called edge refinement, where we reduce edge. You basically do mesh refinement and reduce the mesh edge size. Or we can do p refinement, where we increase the order of the polynomial that we use in our shape function. For example, going to quadratic as opposed to the linear one. That's called p refinement. Or we can also do a combination of both, which is what's called HP refinement. Now, a tricky scenario is this: like, if the error for a mesh with some edge size, let's say we have specify a small edge size, 10 to the power minus 3, and then we get some error, right? So if you look at these two numbers, so an error on the order of 10 to the power minus 6 corresponding to an edge size of 10 to the power minus 3, we might be tempted to conclude that our method is second order accurate. But that's not necessarily true, because we don't know what this constant c is. So because of that, we need really more rigorous approaches for estimating the order of accuracy or rate of convergence of our scheme. And we'll talk about that next. So as an example, for example, if your constant c, which you don't necessarily know, is a very small value, like this example here, then even if you might be getting such small errors for this mesh edge size, but your scheme, if you look at this case, it's really first order. The rate of convergence, it's h to the power 1. Okay, so and that's because of this constant that in this case it's pretty small. So for us to really observe the first order accuracy, we need to have a mesh edge size that's much smaller. Now, the opposite scenario can also happen. We might have a second order accurate scheme, which is pretty good. It's second order accurate. So h to the error is, bounded by h to the power 2, but the constant is pretty large. So essentially, if you have a mesh edge size, for example, h equals 0.1, we're going to get very large error. But the method is still second order accurate. And that's just because of the large constant. So really, in this case, for us to really observe the second order accuracy, we have to go very, very, very fine mesh edge sizes. Okay, now how do we estimate the order of accuracy, rate of convergence more accurate? So we can estimate this p-value in two different ways. In method one, let's say there's a problem that we know the exact solution. So in that case, what we're going to do is that we're going to run the solution with two different edge sizes, one edge size h, another one half edge size. We can calculate the error because for each of these simulations, because we know the exact solution. And we assume that that is equal to c times h to the power p. So that's going to be our equation. Error as a function of h is equals ch to the power p. Now, if I calculate the error for h over 2, I'm going to get this equation, right? So now what I'm going to do is that I'm going to take the ratio of these two errors to kind of eliminate this constant c. So I have the error based on this assumed formula for mesh h size h. I also have the error for mesh h over 2. If I take the ratios, the constant c goes away. I get 2 to the power p, so I can solve for p, which gives me this equation, this log equation in terms of this ratio. So what that means is that if I calculate this r as a function of h, which is nothing but the ratio of the errors for the two mesh edge sizes, which I can calculate, by the way, because I've done the two simulations and I know the exact solutions. I know both error for mesh edge size h, also mesh h over 2. I can calculate the ratio and then use this formula to find the order of accuracy of my scheme. And once I do that, I can go back to one of these formulas and also find this constant. Okay, like this. Now, the second case is perhaps more relevant, and these are situations when we don't know the exact solutions. In these cases, we need to run 3 simulations. Let's say one with h over 2, and h over 4. So our fine scale solution is going to be with h over 4, some mesh edge size h divided by 4. I'm going to call that h bar. And if I define e bar, I'm going to define e bar, which is basically error with respect to my fine scale solution. And that's basically the error for h minus the error for h bar. And when you do that, when you subtract the errors like this, you kind of, so the exact solution you had, so if you, this is basically the calculation done here, you had, which is the exact solution, will go away. So when you subtract the error for h with error from h bar, u hat goes away, so you get the solution corresponding to your mesh edge size h minus your solution corresponding to the fine scale h bar, which is your fine scale solution with h over 4. So basically, this e bar is basically the error of this mesh edge size h with respect to my finest simulation h bar, which was h over 4 in this case. Okay, so now that I have this, I can write each of these errors. So this is ch to the power p minus ch bar to the power p. And h bar is h over 4, so I can plug that in here. And this is the expression that I get. Now, I'm going to repeat the same thing, but now calculate e bar. Remember, e bar was the error with respect to my fine scale solution h over 4. So if I now calculate e bar for h over 2, okay, because I also did simulation with h over 2, then follow the same procedure, I'm going to get this expression. Okay, so now I can take the ratios of these two, and again, the constant c will be eliminated. So I'm going to take this ratio r bar, which is my error with respect to h over 4 for mesh edge size h, divided by my error for the simulation with h over 2 with respect to h over 4. When I do that, this is what I get. 2 over p plus 1. So now this ratio you can calculate. You know that because you have all these 3 simulations. You have the h simulation, h over 2, h over 4. So you can calculate this ratio. And then once you do that, you can solve for p. So from this expression, you can solve for p. And then you will find the order of accuracy for your solution. But just you need to make sure in all of these that the edge that you choose is sufficiently small for your approximation to be accurate.